Hi, question 7.2. Let's look at what we've got. As we've seen in question 7.1, we said the best way to attend to any problem as such when it comes to any of the cycles is to sketch and also to outline the values that have been provided. Sketch the cycle and also outline values that have been provided and the values that are requested. All right, let's quickly read through the question. It says, in an ideal constant pressure, so looking at reading that constant pressure, that tells you straight away that that is a diesel cycle. It moves on to say the overall volume ratio of the cycle is 8:1. 8:1. So what that means is that since it's overall ratio, you'll be looking at the maximum volume and the minimum volume. We'll be able to pick that up from the sketch in a short while. So the maximum and the minimum volume. It moves on to saying the volume ratio of the adiabatic compression is 6:1. The pressure, volume, and temperature of the air at the beginning of the adiabatic compression are 100 kilopascal, 0.084 meter cube, and 28 degrees centigrade. We've also been given the gamma value as 1.4. We've been given the molar heat capacity as well. And then, so as we did for the previous question, we are being asked to calculate the pressure, volume, and temperature at the different points. So we remember we've got 4 points. So as we did previously, we said let's sketch. So the first point is the 1 to 2, which is the adiabatic compression, followed by 2 to 3, which is the constant pressure. That's the point of constant pressure. Also, we know that there's an isothermal process taking place there, but our emphasis, constant pressure. And then let's move on, adiabatic 3 to 4, and then the constant pressure. Our emphasis rather, let's focus on isobaric to avoid any confusion. Constant pressure, let's focus on isobaric there. So from what we've been given, remember it says overall cycle volume. So since it's overall cycle volume, it will be the maximum, which the maximum, looking at this sketch, the maximum is V4. The minimum volume is V2. So if you look here, that is the minimum. So if you draw it there, if you draw this there, that is the maximum. So that's how we get 8 from the question. And then it also says the adiabatic compression volume ratio. So we need to look at the sketch again. Where do we have adiabatic compression? That will be 1. And where do we have adiabatic compression? Let's look at this again. 1, 2. So it's this point. So that's where we've got adiabatic compression. But it also follows, we talked about that in the previous calculation, that always watch out for parallel processes. So what that tells us is that if we have V1 over V2 equal to 6, then it follows that the corresponding, this other side too, 3 and 4, V4 over V3 will be equal to 6. So you can write that down. We'll actually see it clearer later on. V4 over V3 will also be equal to 6 because these are parallel. Remember, as we alluded to, as we saw earlier on, these are parallel. Let me write this here. Parallel adiabatic processes. So the only difference is one is compression, the other one is expansion. So we've taken note of that. So let's start by looking at the PVT at point 1. So point 1, we've been given the pressure, we've been given the volume. So all this we are given, we've been given the temperature. All we need to do, for the temperature is convert it to Kelvin. And then for so convert it to Kelvin, so we have those values. Then it should be based on what we were given here, this. It should then be easier for us to calculate V2 since we have V1. So from there, if you plug that in, we have our V2 value. So the next thing now is for the point 2. So point 2, so point 1 done. Point 2, we have the V2 from that equation. How do we now, what are we left with? It will be P2 and T2. P2 and T2. And what is happening at point 2? We've said it's adiabatic. So if it's adiabatic, we go back to our working formula, pick the appropriate formula, which is this. Which is that. So if you make P2 subject of the formula, you solve that, you get your P value. You get your P value there. So that is P2. Also, we've also been given the temperature relationship. We just plug in the value and we get that, so you can solve for that. So point 3, so how do we solve for point 3? Point 3, let's go back to our sketch. Where is point 3 taking place? It's taking place here. So point 3, moving from, remember we've solved 1 to 2, let's continue the sequence. 2 to 3, it's isobaric. So if it's isobaric, what does that tell us? P2 must be equal to P3. So whatever we've calculated here for our P will be same as P3. So that's for isobaric. So we've gotten that. So what are we left with? We are left with the volume and temperature. But remember, we've said earlier on that V4 over V3 will also be equal to 6 because they are parallel processes, so which we bring in here. So if V1 over V2, V4 over V3 equal to 6, we can call this equation 1, and then we also remember at the beginning we also have V4 over V2 equal to 8, so you can call that a second equation, equation 2. So if you solve for both of them, if you equate them, we'll be able to get our V3. So that's how we got our V3. So our P3 based on the fact that it's isobaric, our V3 using these relationships here based from the from what we are provided. And now moving on, what are we left with? So we have the pressure P3, we have the volume V3. Now we are looking for the temperature. So for the temperature, all we need to do is go back to the formula that we've been provided, and in that formula you see that you can equate V2 over T2 equals V3 over T3. So you can equate that, and if you do that, you get your T3 value. So now let's move on to point 4 to get the PVT values at point 4. First thing, let's go back to our diagram. So we've moved 1 to 2, 2 to 3. Now we are moving 3 to 4. 3 to 4. What is happening there? Adiabatic, expansion. 3 to 4. Adiabatic expansion. So we say P4. Let's look at that again. Point 3 to 4. 3 to 4. So 2, 3, 1, 4. But so we'll see that. And then we have, so P4 is equal to P1. P4 equals to P1. So if you look at this, where is our 4? Where is our 1? Yeah. So remember, it's a constant, it's isobaric. So remember this. So 4 to 1, yes, constant pressure. It's isobaric. Don't remember that. I made a mistake there. So this is isobaric, constant pressure. So P3 equal to P4. All right, so that's how we got that. Okay, so we've gotten that. P4 equals to P1. What else do we need? We also looking for the volume. So for the volume, remember we have this equation from the beginning. We are V4 over V2, and since we have V2 already, we can calculate V4. So that's how we get a V4. This is how we got a P4. Now we are left with the temperature. So how do we get that temperature? All we just need to do is we can remember for anything happening for the Point 4, we can look at the point 4 from two perspectives. We can look at point 4 from this perspective, isobaric, and we can also look at it from that perspective, from the 3 to 4 perspective, adiabatic perspective. So if we solve it from the adiabatic perspective, we can use the relationship, the adiabatic process relationship, which we've been given, which is this, and then we can solve for the temperature. What I want you to try out is this. I want you to try and solve for the temperature by looking at from this perspective, the 1 to 4 perspective. What I've solved here is from the 3 to 4 perspective, this point to that point. But I want you to solve, since we have values for 1 already, I want you to try and solve for the point 4 from this perspective, from the constant, the isobaric perspective. So I want you to try that out and see that if you get the same value as we've got in here. So the next question says heat received. Heat received. If you remember from the class, we've said that heat is received for a diesel cycle. Heat addition occurs at constant pressure. And where's your constant pressure? It's 0.2 to 3. So 0.2 to 3. So this is where it is received. And you might say, but how about 1 to 4? Remember, 1 to 4 is at a lower temperature place. So 1 to 4, so what that means is that what is happening at this point would rather be heat rejection. So heat rejection is what is happening at this point. It is at the upper part that will have heat addition. Upper part that will have heat addition. That's one. Secondly, remember that for constant pressure cycle, heat addition occurs at isobaric process. So that's why so that's what we've got there. So take note of that. And then if we go back to our equations, let's quickly look at that again. Let's quickly scroll back. We've been given for isobaric. There we go. So we've got this. We've got that for the heat at isobaric conditions. So we'll take that equation. Let's take it back to, let's bring it back here we need to scroll scroll down further. Yes, so isobaric condition. So here's the formula, but from the formula, what are we looking for? Change in T3 to T2 given, we've got that. But we also have CP. Remember from the question, CP is provided, but we don't have M. So we need to calculate the M, and then the other, we need to calculate the M as well. So how do we calculate the M? To calculate the M, we also need to go back to what we've got. So for the we've got the T, we've got PV, but we don't have M. So we can use this equation to calculate M, but we still need the R. So you need to then remember, as we said, always look for what you've got and what you're looking for. So let's start from the simplest. The simplest in the sense that we need to look for the R value. We need to look for the R value. And to get the R value, we need CP and CV. CP, we've been given CP. We have this other relationship. Gamma is equal to CP over CV. So since we have CP, we have gamma, which is 1.4. We get our CV. So from there, we can get our R. So we have our R value now. If we plug in the R value here, we can get our M value. So if we calculate that, so this gives us our M, 0.0972. So we can take this. We've got our M. This is the formula we are working with. Plug in the M there. We have the CP, which is there 1.006. And then we have change in T, which will be T3 to T2. T3, T2, and that gives us that. So that's how we calculated that. Let's move on to the work done. I wouldn't repeat this because it's similar to what we saw in example 7.1. So all we need to do is you identify what processes are taking place. We have adiabatic, isobaric, adiabatic, isobaric. So based on that, we pick all the formula we've been given, you pick them and then plug in the values. So once you plug in the values, you should be able to calculate your work done. Remember, anytime it's compression, it will be negative. If it's expansion, it will be positive. So negative and positive value. So take note of that. And then how do we calculate the total work done or the net work done? We add everything. So that is the total work done. So now let's move on to thermal efficiency. So since it's thermal efficiency, let's go back. That means there needs to be, for you to calculate thermal efficiency, you need to look at where heat transfer is taking place. Where heat transfer is taking place. If we go back to our diagram, you see that it's taking place at T1, T2. It's taking place at T1, T2, or T3, T4. Yes. So it's taking place at this T1, T2, T3, T1, T2, T3, T4. So if you plug those in, so either way, it's either you use this or that, you should get the same answer. And the third question we've been asked is the Carnot efficiency. The Carnot efficiency we use, remember, that would be the heat, the place of the heat reservoir and the cold reservoir, so which will be the highest temperature, the lowest temperature. If you plug those in, you get your Carnot efficiency. So that's how we got that Carnot efficiency. And then this second to the last question is the work ratio. For this, as we've seen earlier on, it will be the total work done and the positive work done. So we'll pick the positive work done from this. So what are the positive work done? This and that. We add them up, and then we also look at the total work done. So that's how we got the work ratio. So there. You'll also be given this formula to calculate the mean effective pressure. So let's just plug in the values. We have the net, which is 10.425. We've got that. We have the maximum volume, which is that. We have the minimum volume, which is this, and that gives us the work ratio. So I'd like you to go through this carefully. If you've got any query, anything that you need clarity on, don't hesitate to send me a message, and then we can go through it together once again. I want you to then I haven't looked at example 7.1 and 7.2. I want you to carry the knowledge you've gleaned from those two examples. Look through example 7.3 and also which is for auto cycle. And then I want you to also look at example 7.4. Solve those other examples as your practice questions. All the best.